Quantum mechanics is weird and counterintuitive, but why isn't our macroscopic world like that too? In the quantum world, things are frequently at multiple places at the same time, or at least they behave like they are. But even imagining such a thing to happen in our day-to-day world feels absurd and impossible. And if this is how a world at the most fundamental level works, there must be a way, a process that allows of a definite classical reality to come out from a not so definite quantum physics. Richard Feynman famously said that if you think you understand quantum mechanics, you don't understand quantum mechanics. What he was referring to was not related to how much anybody knows about quantum mechanics. We know quite a bit. Rather, it was about whether or not anybody really understands it. There's a reason some of the most prominent scientists never liked quantum mechanics, because it didn't make much sense apart from the fact that it worked and therefore must be true. It overthrew the age-old notion of definite reality and certainty. Instead, the world was now described as being in all possible states up until the instant we measure it, at which point the sum of all states randomly collapses to any one of all possible states. Electrons, for instance, can be found in two different spin states, up or down. However, before measurement, it isn't clever to think of these electrons as being in a definite state. Instead, we should think of these electrons as having both spins at the same time. The electrons are actually in a state which is a sum of spin up and spin down, something we call the superposition state. But when we try to measure what spin the electron really has, the superposition state collapses to any one of all possible states, which means either up or down, not both. But if all we can know is what we have measured, and we have measured the electron in one of all possible states and not in a superposition, how do we know that before measurement it was in a combined state of spinning up and spinning down in a superposition? Like, how do we know that? Well, the answer is interference. Let me explain. It was well known during the 1920s that things at the quantum level can be thought of as two different classical analogs. It can be thought of as a classical particle sometimes and like a classical wave at other times. This is the famous wave-particle duality thing. The most complicated part was that when we are looking at a quantum object, when we are observing it, it behaves like a particle. But when we are not, it evolves like a wave. Now this doesn't need to be taken seriously, like as we understand things today. Quantum objects are always described by waves, and what they really are is something anyone is free to debate on. Now, there's this thing called the wave function, which is kind of a description of these waves. The square of this wave function gives us the probabilities for any particular observable outcome to be true. Yes, probabilities. In quantum mechanics, everything's described by probabilities. If you've heard Einstein's quote, "God does not play dice with the universe," well, he was referring to this idea of probabilities in quantum mechanics. He didn't like it, believed that the laws of physics should be deterministic and not inherently random. Regardless, what I was saying was that quantum objects behave like waves, described by a wave function. And here comes the fun part. Waves have a tendency to interfere, and interference is key to quantum systems in behaving quantum. Let me illustrate this with the help of the double slit experiment. If you fire individual electrons through the double slit, you get an interference pattern because the position of the electron is described by a wave function which travels through both of the slits. Part of the wave function travels through the first slit and some other part of the wave function travels through the other slit. And therefore it can be thought of as a superposition. And then it interferes as expected from waves. Something we wouldn't have seen if the electron was always in a definite state, because then it must have gone through any one of the slit and not both, and we then couldn't have seen the interference pattern. But then, if superposition states are so common in the quantum world, why does these effects disappear on a larger scale? Why don't we see such effects in our day-to-day classical world? Well, thanks to another really famous quantum phenomena called quantum entanglement. Think about what would happen if two particles interact. They can become entangled. Being entangled means the state of one particle is dependent on the state of the other particle. Actually, there doesn't even exist two different states anymore. Instead, both particles exist in a single state, a combined state. A combined state in which a particular state of one particle corresponds to one and only one state of the other particle, and vice versa. they are in a composite state. Therefore, what ends up happening is that effects such as interference or superposition also become the property of the composite state and not of individual states that previously existed. Let's consider the case when two particles interact and become entangled with each other. Suppose particle A is in a superposition of up and down states, and particle B is also in a superposition of blue and red states. Doesn't matter what these states really mean, I just made it up to clarify a point, so don't worry about it. Let's focus upon particle A. Particle A is in a superposition of up and down states. These two possible states can interfere with each other because these are talking about the same scenario. But suppose now these two particles, A and B, interact in such a way that makes them entangled with each other. Then their individual states lose meaning and instead a composite state is formed of the form particle A up, particle B blue, and particle A down, particle B red. The important thing to notice here is that this is the only state that exists now. Therefore, the only superposition that exists is this particle A up, particle B blue, and particle A down, particle B red. And if you think about it, the phenomena that truly allows us to know the presence of quantumness, interference, can only happen with this combined state, not with the original states that previously existed. Why is this important? Well, consider what would happen if you don't have any information about the other particle. You didn't even know it existed. Then what would be the state of the first particle all by itself? Well, there isn't a state of that particle all by itself. It is not up and down. It is up when the other particle is blue and down when the other particle is red. It doesn't matter whether or not anybody knows about it. Those two particles were entangled and therefore would behave like they're entangled. The point to ponder for us is that if we don't have access to the other particle, we can never tell the original particle is actually in a superposition. Why? Well, the reason we can tell some quantum systems are in a superposition is through the phenomena of interference. But the two original states of the first particle, up and down, cannot interfere with each other. They cannot interfere with each other because they are attached to different alternatives of the other particle, even though we don't know about that other particle. Now the fascinating thing is that there still exists a superposition. There still is happening interference. But with the loss of the other particle, we have lost the ability to see it in the original system. Actually, the other particle, had taken away with it some crucial information about the composite state. If we get all the information about the other particle, we can see the interference effects. But if we do not have all the necessary information to see the interference effects, we can never tell that the original particle is actually in a superposition. Now, how does that answer our original question? Well, till now we were considering a system in which our original particle was only subject to one other particle. But in reality, every system is surrounded by an uncountable number of particles, which could in principle interact with the system and get entangled. We call it the environment. And when our system is entangled with parts of the wider environment, and we don't know the details of that entanglement, it is not correct to think of the particle as being in a superposition. Instead, we should think of the particle as being in a definite state, because with all of those interactions, the system has lost its ability to interfere. And any probabilities that we might get for any possible observable outcome are then just reflections upon our ignorance and not to the intrinsic uncertainty of the system, much like the flip of a coin. And since macroscopic objects are more vulnerable to these interactions, we will quickly lose the ability to see the interference of macroscopic systems and by extension, superposition of macroscopic states. This process of interaction with the environment that turns quantum systems classical and tries to explain the elusive quantum to classical transition is known as decoherence. It is the process by which microscopic quantum superposition stops being in superposition by interaction with the wider environment. An example of decoherence in real life can be understood in terms of quantum computers. Quantum computers use real physical quantum states for computation by harnessing the subtle features of quantum mechanics, such as entanglement and superposition. And instead of using bits, these quantum computers use qubits, which, unlike bits, can be in all possible states at the same time. Since the qubits of quantum computers are also surrounded by an environment, They are also subject to these unwanted interactions. Decoherence then quickly renders these superposition states into definite classical states, which induces unwanted and unpredictable errors in computation. This is why quantum computers are always used in extremely low temperatures, barely above absolute zero. Like, share, subscribe, and let me just know what you feel about the video. That's all I have for today. Thanks for watching. I'll see you in the next video. Bye.